Is that the U.S. government basically has receded a bit and entrepreneurs have the opportunity to do it. Do you think there's some way to recapture the U.S. government's interest in this?
Well, I think if you think back to the kind of the heyday of the 1960s and the Apollo program and all of that excitement, my gut instinct on this is that we as a civilization, we as humanity, pulled that moon landing way forward, out of sequence, from where it actually should have been. It was a gigantic effort with what is, in many ways, it should have been impossible. And they pulled it off with barely any computational power. They were still using slide rules. They couldn't numerically model in computers a lot of these important processes like combustion inside a rocket engine, which is still hard today, but we can do it a little bit. They didn't have computational fluid dynamics to really, everything had to be done in a wind tunnel. Nothing could be done on a computer. So I think the reason we've sort of taken a hiatus, maybe in part at least, is because we pulled that forward to a time when it should have been impossible. And then once it was done, we kind of had to wait and let technology catch up. The reason that Blue Origin and SpaceX and Virgin Galactic and all these companies today, any of these private companies, the only reason that we can do this kind of endeavor at all is because we're standing on the shoulders of NASA, who invented all of this technology. We're still using all the things that they invented back in the 60s. We have refined versions of it. But even the computer codes that we use to validate our designs have been honed and fine-tuned by NASA over decades. So this is, I think we're finally entering, I believe that we are entering a new golden age of space and space exploration. And that the time has come for that to happen because we as a species have up-leveled ourselves in terms of technology. We're ready to do it now. It's amazing that we did it in 1969.
So
it's crazy.
Let's suppose the next...
Liftoff. All right, liftoff, and the clock is started. We've gone for main engine start. We have main engine start.
We are getting confirmation from our affiliate KXAS. It is confirming the Space Shuttle Columbia has exploded over Dallas, Texas airspace. Once again, KXAS is confirming to us that the Space Shuttle Columbia has exploded in Dallas, Texas.
Launch command issued for ignition.
Launch command has been issued. 8, 7, 6, 5, 4, 3, 2, 1.
Set flight speed. Engines at maximum thrust.
And liftoff. It's in 3 seconds into the flight. Everything's still going well. The Soyuz traveling at a speed of about 4,700 miles an hour.
Station, this is Houston ACR. That concludes the KGO TV portion of the event. Please stand by for a voice check from the History Channel.
Now, Ayla asks, after spending time living in space, do you think it actually will be possible for humans to inhabit outer space? And when do you think that's going to really begin?
Well, I think we're inhabiting outer space right now for 6-month durations anyway. And Scott Kelly, of course, stayed up here for just under a year. And we will inhabit, with the moon, I'm sure will be in the future. Of course, Mars is the ultimate target. But Earth is very unique in that Earth provides all of the things necessary to support life. In this destination here in the station, as well as those others that I mentioned, we have to bring the provisions to support life with us from Earth. You know, the air we breathe, the food, the other supplies that we have all come from Earth. So it's, I guess you could say, uniquely provisioned. But certainly it's possible to inhabit places like this. We've shown it for going on 16 years now.
Keynote speaker, Dr. Ellen Stofan, NASA's chief scientist.
President Obama has given NASA a goal of, by the mid-2030s, getting humans to the vicinity of Mars, returning them safely to the Earth, and then sometime following the early 2030s, landing humans on the surface. And so that's NASA's goal, and we're working really hard every day to make this a reality, and we can do it. So you're going to hear a lot about this today, our journey to Mars. Because to do such a difficult thing, send humans that long distance to Mars, you need to do it in a stepwise fashion. So we are working right now on the International Space Station. In the mid-2020s, we'll move out to the vicinity of the Moon, and then on eventually to Mars by the early 2030s. But obviously in the meantime, we're not stopping exploring Mars. We're still every day getting data from our spacecraft at Mars, and we will send spacecraft to Mars in the future. And the road to Mars really does begin at the International Space Station, and I'm going to talk a little more about this later this afternoon. Because to me, one of the hardest parts of getting humans to Mars is coping with microgravity. And that long 7 to 8 month journey back, or to Mars and then back, is a long time for humans to be in microgravity. And that's why Scott Kelly's one-year mission has been so important. And that's why the work that we do every day on the International Space Station is so critical to getting to Mars. The first step toward Mars, you're going to really see, the first step is always going on the International Space Station. But in 2018, we're going to take a giant step forward. And that's when we're going to launch for the first time without a crew, the Space Launch System, our new rocket that we're building to get humans out beyond low Earth orbit, with the Orion capsule on top. That first mission will just go out around the Moon, orbit, come back, descent, and land back on the Earth. But this will be an incredibly important milestone. We need that heavy lift launch vehicle to move humans out beyond low Earth orbit, where we've been now for so long.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid, or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth. 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home.
I want to talk about space exploration challenges that are still in front of us as we go forward. We've solved a lot of them in the past, but there's a couple of key ones that we still haven't solved. And I would say we need your help to do that. So that's what I'm here today to talk about. The other big challenge we have is just radiation in space. There's a field of radiation out there, high energy ions, electrons, all kinds of charged particles. And they're just everywhere. And this is showing the magnetic protection that the Earth provides to these particles. So we're sitting here on Earth, and we have this protection system around us, and the particles can't get to us because, and then we're effectively shielded from that. And right now, there's nothing on the books that says, here, this is what we're going to do, this is how we're going to get there. So the other thing, the radiation challenge is such a big challenge for us, we don't know what to do with it. We have a website that's been set up, and it's the NASA Exploration Design Challenge for Radiation. And they're asking all of you at this website, they're asking all of you to participate. And it goes through K through 12. K through 12, college students, whoever's out there, NASA, and we're all looking for ideas for how we solve that problem for deep space exploration. How do we protect ourselves? How do we shield ourselves? What are the mechanisms? What are the new ideas that could come our way where we could do that?
On my immediate left is Dr. David Newman, who is the Deputy Administrator at NASA. Dr. Newman has her PhD from, and master's degree actually, from MIT, where she was also a professor there for about 25 years, if I understand right. She was confirmed by the Senate last year and began her service at NASA in May of 2015. and her expertise is in the area of aerospace biomedical engineering. So join me in welcoming our guest today.
From San Jose, California, and I was wondering, maybe to both of you, what are some of the challenges that you see coming up in spacesuit design, especially as we think about going to Mars and maybe on to some of the moons, like increasingly hostile environments in space, and dealing with problems of ionizing radiation to astronauts over long periods of time. So I'm just interested in what your thoughts are in that direction.
It's a good preview question for, I think, what we're going to hear about, but go ahead.
Yeah, go ahead. You can go first, I'll go second.
Well, as I had said, the first thing you do is you have to look at the mission. The jump from Gemini to Apollo is very important because the astronauts had to walk. Now with the ISS, the astronauts don't have to walk, so the lower half of the suits are not very mobile. So everything goes to mission. As far as radiation is concerned, that is a concern, and I think David is probably better trained to answer that.
Low weight suits, very low mass, very mobile. That's where the future we think of design and development. Radiation is maybe the #1 showstopper to keep our astronauts healthy and well. I don't think it makes sense to incorporate that into the suit design. It makes sense to incorporate that into your shelters and things like that, because you need a very high dense, high massive protection of the radiation. So I kind of decouple the two, thinking about the suit and life support system design and then your habitat and rover design, which are better equipped to do the radiation protection.
Radiation, we are all scared of radiation, all of us, really. And we are all exposed to radiation, but nevertheless, we are all scared of radiation. Now, if you are scared of radiation on Earth, be prepared. You will be much more scared if you go in space flight. To the point that the question of this talk will be, is this a showstopper? Should we just forget about space because radiation is too high? The problem is not only the quantity, that you get more radiation. The problem is the quality. It's different radiation. We know radiation on Earth. We know X-rays, gamma rays, beta rays, we all know. But radiation in space is heavy ions, iron, these exotic particles, very heavy, very densely ionizing. We say this is a beautiful image that you see. What you see here, this one, is a human cell. This is a human nucleus, so it's 10 microns approximately. And these two lines that you see here are two iron ions that you don't find in space. I'm sorry, that you find in space, but not on Earth, except in Darmstadt, the GSI, where we have it, going through the cells and making damage to the DNA. What do we know about this radiation? We really don't know much, because we don't know it on Earth. We only know it in space, or if you are exposed to GSI by accident. Ourselves from radiation. Well, this is, I want to point out, as my previous speaker, that this is not a girl playing with the sand. This is a serious scientific experiment. It's a serious scientific experiment where this researcher at GSI is trying to measure the shielding properties of the Mars soil. Here it is for you. This is Mars soil. Not really. It's a simulation of the Mars soil, but really looks like the Mars soil. It's identical. It's pretty much the same. So, if you want some, I can sell it for a reasonable price. We even have moon. This is moon soil, which is gray. And actually, this is also showed by the previous speakers. You have these nice caves. So you can go on Mars, you can go in the caves, and you will be protected with this very thick shield. You can even do, this is Mars concrete. These are bricks that you can do with the Mars soil. It's better to use the caves than to dig, because, you know, if you go to a construction site here in Germany, you see that when people are digging, they make a lot of dust. So you can imagine on the moon, where the gravity is 1/6, you really make a lot of dust. So you don't want to do that. But this can be effective if you are on the planet. What about during the transit, when the dose is even higher? You cannot bring heavy shields because, you know, the weight is what is really expensive in a spacecraft. So you don't want to bring heavy shield. Shielding is a very nice solution on Earth when you go to the dentist. Again, not my dentist, but your dentist. Don't go to my dentist because he uses a lot of X-rays and no shielding. Now, your dentist use not so much X-rays and plenty of shielding, but that's heavy, so it's a big you will not solve the problem using passive shielding.
In the 100 years since we discovered radioactivity, we've learned a lot about the negative effects of radiation on the human body. Thankfully, here on Earth, we're pretty well protected. We have an atmosphere 300 miles high, which has a thickness density equivalent of 7 feet.
You can think of active shielding. You can think of electrostatic shielding. I mean, some kind of electrostatic spheres that protect the astronauts. Or even better, you can think to this thing. This is shielding. This is something I think all of you know. This is a beautiful aurora borealis. What is this? This is the shielding of the Earth, the magnetic shielding of the Earth. The solar wind, with these protons and heavy ions, is coming to the Earth, is trying to enter in the Earth, but the magnetic field of the Earth is deflecting these particles. They go to the poles, and then they hit the atmosphere, and you see these beautiful colors. Beautiful. There are many people going there only to see them. You see that the green colors is the oxygen. Sometimes it's more on the red than is nitrogen. So that's how Earth is protecting life, using a magnetic field. So we could think about using the same system. It's not so easy, but it can be done. So what do we do really at GSI? We simulate the cosmic rays. This is this is our accelerator at GSI. We also have many people, 1,000 people working there. We also have lawyers too, not scientists, but also lawyers, mostly scientists. And we can simulate the particle. We need these huge accelerators because the cosmic rays are so energetic. They are so fast. So you need a very large and expensive accelerator to simulate space radiation. But there is a nice part of the story. I told you these particles are so effective. You do remember the little astronauts killed by the cosmic radiation, which is bad if you are in space. But if you are a patient, and if you can take the same particles and you can shoot them in the tumor, not whole body, but only in the tumor, then you can cure cancer. Well, this is done. And not very far away from here. It was done in Darmstadt for many years. Now it's done in Heidelberg. This is a picture of a treatment room in Heidelberg. But they are treating the patients using heavy ions, using carbon ions in this case. So I think this is really fascinating, is the possibility that space research and medicine help each other, you know. That the same radiation which is a problem in space can be a cure for cancer on Earth. So at the end, shall we go to Mars or not? Well, I think I was supposed to give ideas here. It looks like, I mean, radiation is a problem. This is clear. Shielding, passive shielding, can be a solution on the planet, but not really on transit. Maybe the best solution The best idea is to use a magnetic shielding, is to build magnetic fields for the spacecrafts that can do what is done on Earth. So it's not really a new idea. It's the same idea that God had a few billions of years ago when he said, okay, I want to make life, but I created radiation already. What can I do now? Okay, maybe I can make a magnetic field, you know? And you see, it's very effective in protecting the Earth and our life from space radiation. Thank you very much.
If you look at our closest genetic relative to human beings, it would be the chimpanzee. We share like 98+% identical DNA. We are smarter than a chimpanzee. So let's invent a measure of intelligence that makes humans unique. Let's say intelligence is your ability to like compose poetry, symphonies, do art, math, and science, let's say, okay? Let's make that as the arbitrary definition of intelligence for the moment. Chimps can't do any of that. Yet we share 98, 99% identical DNA, okay? The most brilliant chimp there ever was maybe can do a little bit of sign language. Well, our toddlers can do that. Toddlers. So here's what concerns me deeply. Deeply. Everything that we are that distinguishes us from chimps emerges from that 1% difference in DNA. It has to, because that's the difference. The Hubble telescope, these that's in that 1%. Maybe everything that we are that is not the chimp is not as smart compared to the chimp as we tell ourselves it is. Maybe the difference between constructing and launching a Hubble telescope and a chimp combining 2 finger motions as sign language, maybe that difference is not all that great. We tell ourselves it is, just the same way we label our books optical illusions. We tell ourselves it's a lot. Maybe it's almost nothing. How would we decide that? Imagine another life form that's 1% different from us in the direction that we are different from the chimp. Think about that. We got 1% difference and we're building the Hubble telescope. Go another 1%. What are we to they? We would be drooling, blithering idiots in their presence. That's what we would be. They would take Stephen Hawking and roll him in front of their primate researchers and say, well, this one is like the most brilliant among them because he can do sort of astrophysics in his head. Oh, isn't that cute? Little Johnny can do that too. Oh, that's so nice. Oh. In fact, Johnny just did that. Let me get it. It's on the refrigerator door. Here he is. He did it in his elementary school class. Think about how smart they would be. Quantum mechanics would be intuitive to their toddlers. Whole symphonies would be written by their children, and like I said, just put up on the refrigerator door the way our pasta collages are on our refrigerator doors. So the notion that we're going to find some intelligent life and have a conversation with it? When was the last time you stopped to have a conversation with a worm? Or a bird? Well, you might have had a conversation, but I don't think you expected an answer, all right? So we don't have conversations with any other species on Earth with whom we have DNA in common. To believe that some intelligent other species is going to be interested in us enough to have a conversation, they'll look at our Hubble telescope and say, oh, isn't that quaint? Look at what they're doing. So I lay awake at nights wondering whether simply we as a species are simply too stupid to figure out the universe that we're investigating. And maybe we need some other species, 1% smarter than we are, for which string theory would be intuitive, for which all the greatest mysteries of the universe, from dark matter, dark energy, the origins of life, and all the frontiers of our thought, would be something that they would just self-intuit. I'm jealous of that possibility, because I want to be around for those discoveries. Thank you all.